So far we've talked about sigma interactions, where the orbitals meet head-on along the internuclear axis. But there's another type of interaction where the orbitals meet side-on, above and below the internuclear axis. And this type of interaction is called a pi interaction. Again, we have our axis system where the z-axis is left-right, the x-axis is up-down, and the y-axis is front and back. Let's consider what happens when px orbitals interact. Again, there are two possibilities. Either the shading, which represents the sign of the wave function, can match up, or the shading can be opposite. Notice if we bring these orbitals together, they will touch in two places, above and below the internuclear axis. This is characteristic of a pi-type interaction. If the signs match, we should get constructive interference with a bigger positive and a bigger negative. Now, the internuclear axis itself is along the planar node of the atomic orbitals as well as the resulting molecular orbitals. So let's bring these together. Bring them together a little bit more, and notice that the overlap again will lead to constructive interference. We can redraw this with one lobe above the axis and one lobe below the axis. This again is a pi bonding molecular orbital. If the signs are opposite, then when we bring the two nuclei together, we should get destructive interference where they overlap. If we try to redraw this, the left-hand side of the left-hand orbital is essentially unchanged. The right-hand side of the right orbital also is essentially unchanged. But again, it cancels out in the middle. Because of the canceling out of electron density in between, this is an anti-bonding interaction, and it is a pi anti-bonding interaction. We can do the same with the py orbitals, although they're a little bit harder to draw. If we draw them where the signs and therefore the shading match up, we should again get constructive interference. We can redraw this with one large lobe in the front and another one behind. This would be a pi bonding interaction. It's similar to what we saw with the px, except now the orbitals have fallen forward. When the signs are opposite, the interference will be destructive. We'll redraw this to try to show most of the electron density is outside the two nuclei, and there's a node in between. This again is a pi anti-bonding orbital. In summary, when mixing s or p atomic orbitals on neighboring atoms, we get both bonding and anti-bonding combinations. The s orbitals give a sigma bonding molecular orbital with the plus combination. When we take one minus the other, which is the same as adding the negative, we get a sigma anti-bonding combination. When combining p sub z orbitals, the plus combination, where the shading on both orbitals is in the positive z direction, gives us sigma anti-bonding molecular orbital, with most of the electron density outside the nuclei. The minus combination, where the shading on the right has been reversed, gives a sigma bonding molecular orbital where most of the electron density is between the two nuclei. The p sub x and p sub y atomic orbitals give pi interactions since they touch at two places. In the case of p sub x, it is above and below the internuclear axis. For the plus combination, most of the electron density is generally between the nuclei in a pi bonding molecular orbital. For the minus combination, most of the electron density is outside the nuclei in a pi anti-bonding molecular orbital. The picture for p sub y is similar to p sub x, except that the orbitals appear to have fallen forward and the front lobes block our view of the nuclei. Again, the plus combination forms a pi bonding molecular orbital, while the minus combination forms a pi anti-bonding molecular orbital.